Hello, thank you for joining our webinar, Exploring the Frontiers of 3D Printing for Space Exploration. Today, we will overview the impact of additively manufactured electronics, or AME, on the development of space applications, targeting to achieve lighter and more efficiently designed spacecraft. Getting insights from miniaturized sensors and complex circuitry through the success stories and real-life examples of our expert speakers. Today's speaker, we have Dr. Rita Palumbo. She works in the Data Systems, Microelectronics, and Components Technology Division at the European Space Agency. She is a researcher in advanced manufacturing of triple-E components and is developing the strategy roadmap to introduce AM electronics in space. Dr. Palumbo also leads an internal ESA working group in AM electronics, which spans across several directorates and is the organizer of the annual ESA workshop on advanced manufacturing of electronics. Dr. Palumbo's presentation discussed the importance and motivations of investigating AME for the space sector, the game-changing potential for faster development of a spacecraft and an independent supply chain, and ESA strategy for introducing AME into the space industry. Additionally, we have Associate Professor Yang, who is a group leader of 3D millimeter wave and terahertz circuits and antennas at the University of Technology, Sydney, Australia. Dr. Yang's group researches emerging additive manufacturing technologies and radio frequency materials for designing high-performance RF devices and antennas, which can be used in RF communication, sensing, and biomedical applications. Professor Yang's presentation covers the state-of-the-art 3D printed CubeSat antennas, followed by a focused discussion on AME metasurface for CubeSat application. And at the end, last but not least, please allow me to introduce myself. My name is Rafael Del Rey, and I'm leading the application engineering team globally at Nano Dimension. I've been having a lot of fun with electronics for a long time in my career. Now I can also 3D print the electronics. And I will present today the evolution of 3D printed electronics for aircraft and space application. Please, if you have questions, use the Q&A button on the platform, and we will review them at the end of the session of all the presentations. So today, Nano Dimension, leading digital manufacturing into the future, basically is getting towards the true Industry 4.0 solution with additive manufacturing in different areas, from electronics to ceramics to micropolymer, in order to create the manufacturing of the future in which the demand is on the site and not having a lot of inventory. And the vision is to become the digital manufacturer leader through disruption of electronics and mechanical production by applying environmental friendly and economically efficient electronics and precision additive manufacturing for the conversion of digital designs on demand, anytime, anywhere. So all this view is synthesized in replacing all of the steps of the normal manufacturing of electronics, replaced by a few of machines that can 3D print them additively without garbage. So, and because of these very unique components, the innovation also for the space is in systems like RF amplifiers, chip array sockets, optical components, and the glue of them, dispensing and pick-and-play solution to make sure the manufacturing can allow all the components. And now the main presentation, the evolution of 3D printing in space technology. The introduction of 3D printing is been 4 years ago with the first research of three-dimensional objects to be printed. And there were several interesting patents about the technologies to 3D print, like stereolithography, laser sintering, fused deposition model. But everything consolidated until 2006 with the RepRap, first self-replicating 3D printed. And in the last decade, it was very interesting to see the developments for the space, because NASA started 3D printing rockets. And then there was, in 2014, the first piece 3D printed in the space. The design was transferred to the space. And then the dimension started creating 3D printed electronic circuit boards in 2017, and in 2021, there was a design printed with this technology that is flying in the International Space Station. To give the generalities of additive manufacturing, there are 4 main technologies. Extrusion printing, that is basically a plastic bio-ink that is extruded into objects. This is a very simple technology that can be seen in printers that are available for the consumer market. There is selective laser sintering, mainly for metals, that a powder bed is focused with a laser objective, and the beam is solidifying the shapes layer by layer. There's projection stereolithography, where a projection system can be very precise in resolution over a photosensitive material and create shapes, especially with polymers and ceramics. And there's inkjet printing, that is the technology for the electronics, that an inkjet cartridge, just like the paper color printer, is loaded with a polymer and jets this material on droplets, creating the surface of a 3D structure. So in order to see how this technology works, it's probably easier to see with a video. We have a conductive ink and an electric ink. We call them ink to the materials because they are liquid and with very low viscosity. We get first the conductive and solidify by sintering with infrared radiation, and then we get the dielectric and solidify by curing with UV light. And the build starts creating layer by layer the volume of the 3D printed feature. In order to see it faster, it's just making droplets from a digital file that comes from the electronic design, the vector 2D design, and is jetting these droplets, creating layers or slices that are 1.25 micron thick each one, until building the full volume up to 3 millimeters. A cross-section of this can see of the build that can be related to the normal PCB stack-ups. And what is achievable here is to jumping from the classic PCB design with laminates to a 3D circuit that can be printed or manufactured with different shapes, challenging the normal layer by layer. Because passive structures and non-planar transmission lines can be done like twisted pairs, vias in 45 degrees, coils, capacitors, and resonators. And for space, there are some designs like the RF amplifier and antenna that is working in the International Space Station as an experiment to see how good is the material developing there. And also, there is another turnstile antenna for an aerospace application that was designed precisely for having the highest TRL possible with the test. And the shape and form of the antenna makes it ideal to be 3D printed, because it cannot be built with the traditional technologies just because of the cross-section between the turnstile. And this antenna passed all the environmental tests required for aerospace. And it's just by design that this technology can be used for very robust applications. And the most important is the net zero vision, because the ecological impact that we have is zero use of water and a big reduction in CO2 emissions, raw materials, and chemicals, because we are using additive technology and not removing. So the idea is to go with traditional manufacturing, to use one machine, reduce the waste of CO2, water, chemicals, and materials to just what is needed on the site, on the spot, and also reducing the logistics. And now I will give the lead to present to Dr. Rita Palumbo for the topic on the International Space Agency.
Thank you, Dr. Del Rey. So let me share my screen here. Let me put it to screen. Okay, so, well, I don't know if to say good morning or good afternoon, everyone. We have people from all over the world, so which is amazing. My name is Rita Palumbo. I think Rafael introduced me quite extensively, but just to sum it up again, I work at ESA. I've started this work actually last year. My background is in aerospace engineering, but now I'm doing this work on developing a strategy roadmap to introduce advanced manufacturing of Tripoli components to space. So let's start. I'm based in the UK, so I don't know how many of you are familiar with the European Space Agency. We have sites in many European countries. Not a lot of people know that we also have a site in the UK. So I like to show this slide to show where I am. And basically, we are located on Harwell campus, which is an amazing campus with over 200 companies, different types of businesses in different types of sectors. But among these, we have the space cluster. And so as part of the space cluster, we have ESA EXAT based on this campus. So just to show a quick outline of this presentation, first of all, it's a very top level presentation. So we won't go very much in the technical details. I will keep it, let's say, from a motivational point of view, why we're doing this, what we want to achieve, what are our biggest reasons for exploring this. So I will give a brief introduction because we have a very varied audience. So just to introduce what AME is, what is a vision for AME, technology gaps, then I will show a draft of our roadmap and some remarks and conclusions. So to start, first of all, I want to say that just to clarify, we call it ESA AME, Advanced Manufacturing, which is different from what Nana mentioned or other companies in the printed electronics industry usually call AME, which is additive manufacturing. So in our way of talking, additive manufacturing is included in the advanced manufacturing methods. So for advanced manufacturing, we really include anything that is not conventional. It can be additive or it can be subtractive. Truth be told, the vast majority of these new technologies are additive, so such as printing or 3D printing. And just to show a quick clarification of the different types of additive manufacturing technologies, they can be categorized in contact and non-contact. So contact technologies are usually those that are usually roll-to-roll or sheet-to-sheet. So it means that we use direct contact with the substrate to print what we are trying to print, our circuit or component or whatever it is. And usually, so these are by direct contact. They are, as you can see in this picture, this is one of the machines by Quatema. They're usually very big equipment, so they require a lot of infrastructure, usually for mass production, and they usually analog methods, which means that to change what we're printing, we need to change a physical part in the machine. Whereas non-contact methods are usually methods where the ink is transferred to the substrate by a nozzle. They're usually slower than roll-to-roll, but allow to really produce on demand, so a low volume production. They don't require a lot of tools, and they're usually digital. So you can see some of the examples. Of course, there are plenty of examples on the market now, but these are just some of the printers. And then in terms of the final products, of course, sometimes there is a confusion, and printed and flexible electronics go together, but really it's not really the case, because you can have electronics that are printed and flexible. And this is a lot of the roll-to-roll, for example, goes in that category. But you can have printed electronics that are rigid. So, for example, what Nano mentioned that, or Elephantech, other companies like Enscript, there are plenty of companies out there that are included in this area. You can have flexible, which is not printed. So, for example, where still the conductive layer on the flexible substrate is manufactured by removing material, so via etching. And then, of course, you have the rigid, not printed electronics, which is established PCB and electronics manufacturing. So in terms of our vision, quite straightforward. We want to introduce AME to space because we see big potential. I will show you in the next slides the motivations. But what we are trying to do, and our goal is to facilitate the industrialization of AME techniques and the development of a European local one-stop shop supply chain for sustainable, fast, agile, and digital manufacturing of electronics and components. So this is our main motivation here. And we are planning on doing this by leveraging the technologies that already exist, so terrestrial technologies, and developing processes which can be certified, that can be repeatable, reliable, so that they can be used for space applications. And this is in support of the ESA Agenda 2025 technology strategy, the ESA's journey towards sustainable electronics and European industrial competitiveness. Also to say that I'm leading, I think Rafael mentioned it, so I'm leading a working group at ESA that's a working group spanning many different directorates and many different sections. We understand that this work is very multidisciplinary, and we want to have a holistic roadmap that really encompasses like very different fields of application as well. And so we are doing this work together in a very, like I said, from a very top level, trying to push for different applications, whether it's for space transportation, for human and robotic exploration, Earth observation, connectivity and secure communications, and so on and so forth. So this is also very important to consider. Now, in terms of the motivations, there is a big list here. This is a very important slide, I think, in terms of why we are doing this, because bringing change is never easy. Bringing change, it's always difficult. It's like, why should we change something that works already? And that's perfectly understandable. So it's important to understand why we want to do this. And AME, we believe, offers game-changing advantages for the high variety, low volume space industry and for prototyping. So space industry doesn't need mass production. And a lot of time we have to wait even up to a year to get a few components, for example. So this is something that really slows down the whole spacecraft development time. And that's why techniques such as digital printing can be so game-changing for us. So first of all, digital manufacturing supports ESA digital transformation of the design process. And of course, there is also the possibility of integrating with AI, with digital twins. Then, like I mentioned, the possibility of having on-demand, rapid, agile manufacturing reduces the procurement time from months to hours and allows to quickly react to market needs. Then there is, of course, the possibility of developing an independent European supply chain for electronics and components. So we can really push this to develop European sovereignty of manufacturing of electronics. The costs can be reduced up to a factor of 10. You can have 70 to 90% weight reduction, up to 86% reduction in environmental impact. The access to the Z dimension allows unconventional configurations, any shape, any substrate, miniaturization. You can even think about embedding electronic functionality into the structure, for example, the walls of a satellite. And then overall, easier manufacturing, simpler packaging, and monolithic integration. So now I just want to spend a couple of words about the concepts of innovation. One person a few years ago actually said that the biggest mistake you can do with 3D printing is duplicating an existing design. And this was Tommaso Ghidini, which is the head of our the current head of the mechanical department at ESA, during his TED Talk in 2015. If you haven't seen it, I highly recommend it. So he was talking about additive manufacturing for structures, right? It's what our Tech M department as the work that they've been leading for the last few years. And the idea is that with printing, you want to think novel. You don't want to just duplicate whatever exists already, because otherwise you're just wasting the potentiality of printing. And so if you observe nature is additive. And it's important to see how with printing we can simulate this, with printing we can add material instead of remove material and imitate the most efficient process ever that nature does every single day. And even if you look at from a structural point of view, of course, this doesn't apply strictly to electronics, but from a structural point of view, you add material only where you need in nature. So you see that the points that need more strength are thicker. And this is how nature works. And so with advanced manufacturing of structures, that's what they've been doing. So they've been developing these types of geometries that really put materials only where you need. And I think that we basically need to be doing the same thing with 3D electronics. I don't mean doing the same type of structures, of course. I mean that we need to learn to think in 3D also for electronics, and to not just copy what already exists, but to develop new designs to make full use of the potentiality that printing has to give us. And so, you know, because I've heard this a few times when you introduce printing, it's okay, let's just replicate what we have, so that we can have all the benefits of having it local and, you know, sustainable and everything, but you're really missing out on a lot if you don't rethink the designs as well. And so the pivot to AME is not easy. Like I said, change is always challenging, but the payoff can be enormous. And I hope that I convinced you in the previous few slides. I also want to highlight that AME aligns with overall ESA goals. So ESA has an Agenda 2025 and has developed a technology strategy. It's usually updated every few years. And we're really aiming at improving the development time of spacecraft. We want to improve cost efficiency. We want to have faster development. And so of course, a lot of the things that we use in a spacecraft is electronics. So if we can push the electronics development, we can decrease the development times, we can reduce the procurement times, we can really help with all these other bigger factors as well. ESA is also developing a green agenda, so called EGA. EGA mobilizes all of ESA and the space sector to contribute to the climate neutrality of Europe. And in fact, it will soon provide training for all ESA engineers to introduce LCA and eco-design principles in all phases of mission design. And so printed electronics are a big help in this direction, because there are several reasons. First of all, printing is, like we mentioned many times, is additive. It means that we don't remove material. We don't have waste of material. We don't have discharge of material, of toxic material, even in water. There is less energy consumption, less manufacturing tooling, less hazardous substances. The supply chain is simplified, which means that you also have reduced transport footprint, 70% weight reduction. Also, digital manufacturing allows implementing concepts such as circular economy. And so these are all factors that really show how at this stage where we are rethinking everything, we should start to include printed electronics or advanced manufacturing of electronics to help in this direction. Now, just mentioning also the technology gaps, because of course we understand very well that this is a very low TRL technology still, and especially for space, we have no idea about space compatibility. So a lot of these techniques, of course, will have low accuracy and resolution. We know that most printing methods allow feature size bigger than 10 micron. Except a few printers such as XTPL or electrohydrodynamic printing, or the technology by Hamming, which allows to go to the nanometer scale. But most of the printing methods still is at higher feature size. So it's important to see that this, of course, limits some of the applications. And also the low mobility and device density makes it difficult to fabricate high performance components. And so at this stage, we understand that hybrid systems, which integrate AME with traditional electronics, are so far the best solution. And I think that this is what we should pursue, at least in the short, medium term. And then there can be sometimes problems with high roughness that can limit high frequency RF applications. Standards for reliability and repeatability are still under development. And of course, for space, it will be a whole other chapter that we need to consider and develop. And there is no very limited space heritage at this stage. Now, in terms of the roadmap, I just want to make it clear that what I will show you today is a draft. And I'm working on this every single day. It's part of my work as a researcher. So it's an ongoing work, still very much open to input and really, like I said, changing every single day. But so far, so it looks like in terms of priority areas of application, small satellites are the biggest area, because miniaturization for satellites is what is really pushing the space industry in the last few years. And of course, among the satellites, if you see, the vast majority are for communication and for Earth observation. So we believe that these two areas in particular might be the most promising areas of applications of printing electronics. And again, for small satellites, intelligent management of space is crucial, because they're so small that, of course, sometimes it's even difficult to put basic functionality into these satellites. And what you can do, like if you're actually able to embed the electronic functionality into the walls of a satellite, you will free up a lot of space for payload. So this is something that could potentially be game-changing for this application. And also exploring applications for constellations could be a great platform to explore AME, because constellation operators replace each deorbiting satellite within years to include new designs which are based on the latest technology developments to introduce new capabilities. So this could be the perfect opportunity for that. And of course, then the advantage and the promise would be higher density, weight volume optimization, more space available in the satellite, and possibility to print locally on demand and quickly adapt to market needs. Of course, these are not all the applications. We see a lot that could be used for human and robotic exploration applications, HRV, in terms especially of integrated sensor systems used for various means. Also in space manufacturing, soft robotics. We see a lot of potential for launchers and for space transportation in general. So for example, printing the harness cabling. And for the rollable solar cells, in fact, even for satellites, we already have it in our roadmap for some of our sections that do this type of work. Now, this roadmap, like I said, it's a draft. It's still every day changing, but so far the idea would be in the short term to focus mostly in applications that are for telecoms and Earth observation satellites, and then start with low TRL activities in other areas. And as we go pushing this to through the print industrialization and then industrialization and qualification of all these technologies, we see the success marker and in-orbit demonstrator in the medium term as well. So I'll try to be quick because I think the time is almost over. So some final remarks that I want to say is that in general, in printed electronics and in advanced manufactured electronics, everything goes together. So you have, of course, you can have a certain area of application, and then you go to the systems, products, components, materials, and substrate. You can't decide one thing independently from the other factors, but in AME, all go together. So the right materials are chosen for the right process, for the right application. And at this stage, so I think I've showed you enough that we have the motivations and a solid vision for this. We are finalizing the roadmap. And right now we are in a phase where we are gathering ideas for real systems products applications. So we are very much open to input. There may be a budget, but we need input, especially from space primes, to understand what are the real applications in terms of systems and products that they see or that they would need to set up programs and solidify then the short and medium term goals in our roadmap. So if you want to contribute at this stage, defining where we're going to head in the next few years, do get in touch. And then another highlight would be that just to show you that we are quite serious on this, we are also having our first ESA workshop on advanced manufacturing of electronics. This will be next week, hosted in the Netherlands, our ESTEC site, and it will be a yearly appointment. So you can keep the eyes out maybe for the one next year. And finally, just to conclude, so I think I've showed you well enough that advanced manufacturing of electronics and components promises to be a game-changing application for the space sector. The high variety, low volume space industry is particularly benefiting from the advantages of AME. And some of the top benefits include short procurement time, independent European supply chain, sustainability, low costs, miniaturization. The areas that we see as of the highest business interest right now include small satellites for telecommunications and Earth observation. But of course, we're open also to explore and include applications in other areas, maybe starting from smaller activities or in the longer term. So applications in human robotic exploration, space transportation, and other ESA programs. Tech ED, which is my division, is collaborating with another division. I know it's a lot of acronyms. So Tech MSP is the section that deals with materials and structures, basically, and is introducing a long-term roadmap to support and facilitate the industrialization of AME technologies. And these activities will be based in EXAT in the UK, so in our World Campus, which I showed you at the beginning of the presentation. And finally, like I mentioned, space primes are invited to get in touch to discuss real applications and needs and to support the setup of AME projects. So this is it. Thank you so much for being here, whether you're here live or you're watching the replay. Thank you so much for your attention, and you have my contacts on the screen as well.
Thanks a lot. Next is the turn of Professor Yang with the topic about RF components and antennas for CubeSat applications.
Okay, thank you very much, Dr. Ray, and thank you very much for having me here. My name is Yang, and I come from University of Technology, Sydney in Australia. So today, my topic is about 3D printed meta-surface antennas for CubeSat applications. Let's have a look. Okay, so my talk covers pretty much 6 sections, and from the background about what is CubeSat antennas and the CubeSat systems, and then we discuss about the motivation why we use 3D printed meta-surfaces for the antennas. Potentially could be used for the CubeSat system, and then we have a look of the reason why we use AME for this kind of designs, followed with a couple of design examples and the applications. So background. Okay, so I trust most of the attendees here are already familiar with the CubeSat concept, right? So actually, the CubeSat is actually a class of miniaturized satellites with a form factor of 10 centimeter cubes, as shown here on the right-hand image here. They can be by using more and more of those kind of cubes, and you can increase the volume of the satellite. So advantages of those kind of satellites actually because of the low weight, the lightweight and the low volume capabilities that could be easily to be launched to the space. As introduced by the previous speaker, Dr. Palumbo. So there are a lot of advantages of this kind of satellites in the space by using especially 3D printing technology. So this is one good example that we can see developed by NASA a few years ago. It's called the Rain Cube. That's the first active radar applied for the CubeSat applications. you can see that actually the antenna system here plays a significant role here. For this design is a parabolic one, and it's very light, and launched in the space in 2018 and burned up in 2020. Because this is the first time people tried to prove the concept that those kind of active radar can be built into the CubeSat antennas. So if you're interested in this kind of antenna system, please look at those the report published a couple of papers by the research group from NASA. Um, by by definition, actually, CubeSat antennas can be classified into three groups based on the level of the antenna gains, namely the low gain antennas, medium gain antennas, and high gain antennas. Among those groups, actually, the most common ones are the high gain antennas because for the space communications or sensing, the link budget is always important to work out. So high gain antennas can efficiently improve the link budget and can reduce the power consumption of the satellite system. So here are some definitions about the different different groups. So for any gain lower than 8 dBi, it's called low gain antennas for the CubeSat. And anyone above 25 dBi are the high gain antennas. But they have very different physical shapes based on the antenna types. So you can see that for the low gain antennas, most often they are not very big and they are not big arrays. But for the medium gain and high gain antennas can be the arrays or even meta-surfaces antennas or arrays, even patch arrays. Here I summarized a couple of the state-of-the-art high gain antennas you applied for the CubeSat applications. You can see that they can be the patch antenna arrays or reflect arrays or meta-surface or the parabolic shape. So in general, they are not small, and but most of them can be 3D printed, and because of the requirement for the CubeSat scenario for the customizable to be packed into the CubeSat format, and also they're supposed to be flexibly designed to be fit into the CubeSat system. So here are some of the 3D printing technologies, advantages and disadvantages about the 3D printing technologies for CubeSat applications. So I wouldn't say the disadvantages, I would say the challenges, because um, the they are those actually those are the challenging part for the 3D printing, but that doesn't mean that they are not achievable. Still, that people can achieve those kind of 3D printed, for example, the folded or deployed lens antennas or the antenna arrays. And but there are a lot of challenging practical considerations when you considering putting them into the CubeSat and including the deployment later on after launching. So the moderate the big consideration here is how to print the conductive dielectric multi-material structures at the same time. So some people they use a metal coating after printing the dielectric materials. Some they use some other post-processing techniques. But we feel that AME could be one of the best technologies that can achieve the multi-material printing at the same time. So which means there's no post-processing requirement. Okay, there are many of the papers or reported public works in the public domain, so you might want to look at those state-of-the-art works. Okay, so let's have a look at the motivation. So additive manufacturing actually is not new, and people already know the advantages listed here. So in terms of the AME antennas or 3D printed antennas, what we can find here is for the traditional multi-layer antenna structures, people usually use the multiple PCB structures and stacking them together with the post-processing. But with AME, we are able to achieve the multi-layer structures into a single substrate, as shown here. There's no post-processing requirement. It's just a single-stop printing process. So let's have a look at why we additively manufacture the metasurfaces. So metasurfaces are another concept that if you work in if you are RF engineer or microwave antenna engineer, you might be already familiar with this concept. So metasurfaces comes all the way from the one-dimensional to three-dimensionals, as shown here, introduced in this paper. So the 3D metamaterials or three-dimensional metasurfaces can be quite complicated. So most often we find that the 3D structure might not be easily achieved using traditional manufacturing techniques, regardless of the additive or subtractive manufacturing technique. With AME, we proposed some interesting structure can be used for 3D meta atom for the 3D metasurfaces design, as shown here. So if you look at this image on the right-hand side, this is one of our recent work that we achieved by using the three-dimensional concept to achieve the unit cell for or meta atom for the metasurfaces. So for each unit cell, we have a very interesting structure. If you look at this 3D meta atom, actually it contains the circuit antenna concept. So for the circuit part, it's pretty much we use the phase delay lines to achieve the phase shifters, which are highly integrated into the unit cell here. So if you look at the 3D structure on the right hand, the metasurface, the inside of the metasurface structure could be very complicated. You can see a lot of phase shifters actually distributed in a single substrate. But actually, if you look at the sample, they are very, very thin. So that means AME gives us a lot of design flexibility to achieve very complicated structure that may not be easily achieved using the conventional manufacturing technique. Okay, after we understand why we use AME for the metasurfaces or antenna designs, then we have a look of our recent progress. So using AME, we proved the concept by achieved quite a few RF electronics designs for especially for the metasurfaces. Those kind of metasurfaces can achieve the shaped beams like the vertex beams or collimated beams, or on the metasurface can be used for generate multi beams or for different applications purpose. And this one showing on the right corner here, that's a reflect array and could be potentially used for satellite applications, CubeSat applications. And instead of the metasurface antenna designs, we also verified that AME can be used for achieve very compact microwave circuits. For example, the bandpass filters, couplers, or any other RF electronics can be integrated into the RF front end. So this is really interesting because I think it's advantage for AME, as mentioned by Dr. Palumbo previously, because CubeSat requires lightweight and compact arrangement of the RF components to be built into the cubes. As shown here, I borrowed this image from James. You can see that this AME gives a possibility to achieve those kind of purpose, especially for CubeSat applications. So let's have a quick look of the 3D printing process that we applied by using AME, because this is very important for every designers. So the design rule shown in this slides gives you a general idea about what kind of devices you can achieve, right? Because the printing resolution and the achievable dimensions of the traces and the spacing will be important for the designer. So the latest AME technique we use here is the 75 micrometer, which is based on the Dragonfly 4. So I wouldn't read out all of the design rules here, but you can see that it's very crystal clear that for the engineers to achieve to refer for their design. So here are the key parameters we consider when we design the emitter surface or the RF electronics. So pretty much you can see the resolution is 18 micrometers. So that's pretty good for the most of the frequency band for the satellite communications. And you can see that those spacings 75 micrometer. That's very good. And it's also compatible with BGA patches, and so there are a lot of possibilities by using AME. So this is just a one-page illustration about how we achieve those kind of complicated structures by using the layer by layer prototyping technique. Yeah, very interesting here is that we can even 3D prototyping the metallic wires inside the substrate. You can see here. Okay, design examples. So I probably just give some high level introduction about those designs because we are running out of time. But those actually most of the designs are published, so please feel free to refer the technical details from those papers. Okay, here the first design example is about the dual beam metasurface designs we achieved by using this concept antenna circuit antenna concept. So the for the metasurface, from if you look at the top and bottom view, you can't see what's inside the substrate. Actually, we have a lot of details in the metasurface substrate. Actually, for example, the phase delay lines or the or some other circuits we will introduce later. So by applying this kind of concept, we can generate, for example, the dual beam, dual beam, the dual beam designs with the collimated beams. Both are actually circular polarized. This is another example that we achieved for polarization conversion and to which can convert a polarization with certain angles from between the input and output waves. So we can also shape the beams to make it the vortex beam or collimated beams based on the applications. And this design, we apply the Poincare sphere concept that to achieve this two pairs by using the two pairs of differential feeding lines. You can see from here, very complicated. Yeah. So this is gives a little bit more details about the metasurface design, and you can see from for the metasurface in my fingers actually, that's just only 1 millimeter thickness. There are some other designs like for these designs actually sharing the same polarizations, regardless if it's the right hand or left hand polarizations, they can share the same aperture. And these are the fabricated prototype. You can see that it's pretty, the surface finishing is pretty good. Here are the orbital angular moment beams we generated by using the AME metasurface antennas. You can see the different modes from the mode 0 to 3 with different topological charges. And other than that, we also achieved the bandpass filters, very small. If you put a filter on the finger, it's only yeah, it's pretty tiny. And you can see the bandpass filter response, pretty good. This is another bandpass filter we achieved in the microwave range. This is a coupler that we 3D printed, which can be used for the RF transceivers. So applications. So I'd like to share this video with you so that you have a better understanding about why we use metasurface for the potential CubeSat applications.
Metasurfaces are two-dimensional materials that have attracted significant research interest in recent years owing to their unique ability to control electromagnetic waves. They consist of arrays of meta-atoms, or artificial structures smaller than the wavelength, arranged in a precise pattern on a flat surface to modulate the phase of electromagnetic waves. Conventional Pacharatnam-Berry methods often alter the spin of waves, a property linked to polarization or the orientation of electric and magnetic fields constituting a wave. Maintaining spin states is, however, crucial for their practical applications, such as those in satellite communications for transmitting and receiving data. In a new study, Associate Professor Yang Yang's research team at University of Technology, Sydney, productively collaborated with the engineering team at Nano Dimension to develop three-dimensional or 3D polarization-maintaining metasurfaces using a novel multi-material additive manufacturing method. The 3D metasurface consists of 64 different types of meta-atoms with fixed and rotating dual polarized antennas at the receiving and transmitting ends respectively, connected through phase delay lines. Varying the length of these lines introduces 2π phase shifts for both left-hand circular polarization, LHCP, and right-hand circular polarization, RHCP inputs. The two phase-shifting degrees of freedom can be combined to independently control the LHCP and RHCP wavefronts, while the output spin state remains the same as the input state. Furthermore, this novel design can be swiftly optimized using a pattern search-based algorithm. In the future, this multi-layer additive manufacturing approach can augment the development of polarization-maintaining metasurfaces with multi-layer configuration, which is impossible to achieve with traditional fabrication technologies. Ultimately, these 3D metasurfaces can revolutionize the development of next-generation high-speed microwave electronic devices.
Hey, thank you for watching. We are running out of time. Sorry for that. My talk actually covers the focus on the discussion about metasurface antenna designs potentially used for CubeSat applications, and we proved the concept and about the metasurface antenna designs using AME, and we also demonstrated a couple of designs for different application scenarios. So our next stage will be the system integration and the test in the lab environment, and we're also looking for the opportunities to collaborate. Acknowledgement goes to the collaborative team between UTS and Nano Dimension, and these are the test environment at UTS. Thank you very much. Dr. Ray.
Thank you very much, Professor Yang and Dr. Palumbo, for your presentation. Remember that if you have questions, please post them now into the Q&A. There are some that we can answer them live. Some of them have been already answered, but I will mention them again. Wes Laquer was asking if there are resistive materials on the roadmap. At the moment, the R&D of Nano Dimension is currently focusing on higher performance dielectric materials. And well, your question follows up to a broader discussion, so we will contact you later. There is also a question about the gain difference between a copper-built antenna and a silver ink antenna, given that they have different conductivities. If I'm not wrong, the dielectric is also an important part of the equation on antennas, but according to the test of the specimen in the presentation, it measures less than 0.5 dBs of difference to a normal antenna of the same design and measure up to 9 gigahertz. There is a question for Professor Yang. From Ivan Revenga Riesco. Has your group explored conformal 3D printing and conformal antennas?
Hi, thank you. Thank you for this question. Yes, we are working on the conformal antennas. but remember, we have to follow the design rule that listed in the one of the slides I presented. So there are some limitations you have to be aware of, and definitely the conformal antennas is something that we are looking at the moment.
Okay. Next question is not addressed to somebody, so probably Professor Yang can answer. Could we use phase change materials to achieve solid state meta atoms capable to manipulate the phase?
Yeah, that's a very good question. Yes, so in theory, it's possible. We can use phase changing material. That's something very, very interesting in recent years to achieve that tunable or functional metasurfaces designs. That's I think there's a big potential to be using this kind of materials for space applications because for traditional, there are many other application scenarios requiring those kind of it could be passively driven. The beam, for example, the beam steering or the functional switching um, functions can be done by the phase changing material. Yes, you are right. This is a very good direction.
Okay, here's a question for nanodimension. If the loss of the electric ink is still 0.018 or nanodimension has achieved new ink with lower loss. We launched a new material that is focused on standard reflow temperatures and has a better dielectric performance. But we also have in test in the roadmap better materials with lower losses. So please stay tuned. There is another question for Professor Yang, if you have ever tried to print DNG materials using AME.
Thank you for the question. The answer is not yet, because we use a lot those kind of metasurface designs we achieved actually were based on the Dragonfly LDM and Dragonfly 4 systems that we haven't my team at UTS we haven't played with other materials, but of course we can try the different inks for achieving the other functional materials, but I think that could be a different printing system. I hope I answered your question.
Here is a question for Dr. Palumbo. What happens with the replace the orbiting satellites? Are they being recycled?
So, okay, I mean, I'll answer briefly because it's not pertinent to the topic of today. But I mean, the orbiting is like a big problem, and space debris is something that is in ESA Agenda 2025 because obviously it is a problem. So we are working on it. There are problems. I don't think that at the moment there is a recycling of the orbiting satellites, but it's something that ESA is working on.
Thank you. Here is another question for nanodimension. There are two related, so I will answer both from Paul Talon and Stefan Lovas. If there has been testing to outgassing, direct test for vacuum or exposure test to hard UV radiation as found in orbit. So the answer is yes, there is outgassing test according to the ASTM 59515 standard. That is specified in our data sheet we can share with you later. But also the design from the amplifiers shown in this presentation went to the International Space Station to collect this data in microgravity environment and the UV radiation test. Here is another question for Dr. Yang. What is the operating frequency band for dual beam metasurface?
Thank you for this question. Sorry, I missed this information in the presentation. The dual beam metasurface designs was done in the X band, so it can be achieved in other frequency band based on the application.
I do have a question for Dr. Palumbo. If you are planning to send applications to the space soon, all of these tests that you 3D print in your lab.
So if you're planning on sending to space,
Test
the ISS, I mean, so this is that we do want to have an in-orbit demonstrator in the medium term, because obviously one of the biggest things is understanding, okay, but what happens when we test these things and what happens when we actually put them in the space environment. But before we get there, we will start with some basic investigations on Earth. So testing outgassing, radiation, vibration, thermal cycling. Once we define the applications and the materials and manufacturing processes that we need for those applications, then of course, testing for space compatibility is #1 priority. And then, yes, at some point, we do want to have definitely a demonstrator in space as well.
Thank you very much. It's time to leave. Thank you all for joining. Thanks a lot for our panelists, Professor Yang and Dr. Palumbo. You will receive the recording, and we really appreciate your time and sharing here. All the questions that were not answered, we will contact you later with the experts. Thank you very much.